Okay, let's have a look at the prime factors kata, and we're going to do it in the TDD, which of course stands for test driven development way. What is prime factors kata? What are prime factors even? Well, prime factors are the prime numbers that when multiplied together, so these are factors, make up any positive integer. All right. So, for example, 140 is equal to 2 times 2, which is 4, times 5, which is 20, times 7 is 140. And any positive integer can be disassembled like that, well, apart from 1, because 1 by definition is not a prime number, and a prime number is any number that only divides by itself. And 1. Okay, like 7, for example, can't be divided by 2, 3, 4, 5, and 6, but it can divide by itself. 7 divided by 7 is 1, and of course it divides by 1. 7 divided by 1 is 7, so 7 is a prime number. So yeah, the prime factors of 140 are 2, 2, 5, and 7, and we want to generate that list. We want to find an algorithm to get, for any given positive integer, the prime factors. All right, and how we're going to do this? Well, we're going to do this the test-driven development way, and it's just useful to quickly recap what TDD is, sort of the fundamentals of. There are these things called the 3 rules of test-driven development, and I'm just going to quickly recap those here. We're only going to write production code to make a failing unit test pass, which of course means we're not allowed to write any production code before we've got a test. We have to write a test before we can write any production code. So even when we haven't got any code at all, not even a class and its method, nothing, we would write a failing unit test first. And it's like, how are we going to do this? And we're going to find this out. We only write just small enough of unit test to make the test fail. So we write sort of the most minimal kind of unit test to make the test fail. We don't write a huge beast that tests a huge amount of a particular workflow or something like that. No, we just extend it little by little. So only write enough of unit test to make the test fail, and only write enough production code to make the failing test pass. That rule number 3 is all about keeping the code as simple as possible. It's easy to overcomplicate things. As developers, we like complexity. Well, humans like complexity, and we need to, TDD helps us here counteract that complexity. All right. And this is the life cycle of TDD. We start red, so we've got a failing unit test. That's what red means. In our integrated development environment, our IDEs, a failing unit tests usually come up as red. So it uses like a traffic light type system. Okay, so red, the unit test is failing. Then we proceed to make that unit test pass by writing some production code, so that then the test turns green. And the final step in the iterative cycle there is we refactor, and that means that we will improve our production code. Okay, so the non-test code, the code that actually does something useful, and we will also refactor and simplify our unit test code. All right, we'll may try and simplify that as well, because our unit tests should read, be eminently readable and super easy to understand. So the more, they've got a great name, it's nice and concise, everything that isn't relevant to the unit test is hidden away. Only what's actually important to the test is shown is, of course, important. And then once we've done the refactor step, we kind of go to red again. We either make an extending change to the first unit test and turn it kind of red again, or we write a second unit test that now is red. The first one is still green, hopefully, and then we make that guy pass, and we kind of go round and round. The beauty, of course, is here that if we ever end up in any kind of trouble where we kind of can't see the the forest for the trees, we just kind of go Control Z a few times and we're back in a green state. All right, and we can kind of look at maybe approaching the problem that we've got differently. Okay, oops, all right, a little bit too far. Let's move over to Visual Studio and see what we've got there. Okay, let's do this prime factors kata. So I've got a kata solution here. I'm going to create a test class, and I'm going to call it prime factorizer tests. Oops, tests. There we go. I'm going to call the class prime factorizer, internal class prime factorizer tests, and fact. So I like to use x unit rather than n unit. So they use the fact attribute to denote a unit test. We haven't got our prime factorizer class yet, okay, or a method on that class either. Well, if we haven't got the class, we won't have a method on it. So what do we need to do? What kind of unit test do we need to write to force us to create the prime factorizer class? Well, how about something like this? So public void can instantiate or create prime factorizer. Lovely. And here we're going to say var factorizer is equal to new prime factorizer test. Okay, no, that's not what I wanted. Prime factorizer. I was complaining up here. Class must be public. Yes, public. Lovely. Okay, so we don't have a class prime factorizer. Our compiler is complaining. It's saying, hey, we haven't got, we can't resolve prime factorizer, so why don't we create it? And okay, I'll create it in a separate file. Normally for start I create it in the same file, but you know what, I think it might be easier if we create it in a separate file. Here we go, prime factorizer, internal class prime factorizer. Yeah, okay, internal class will do the trick. We don't need these using statements. And well, the unit test compiles and it will also run. It doesn't there is no assertion or verification statement. This is just a scaffolding test that ensures that we've got a test to stand up the class. Okay, so far so good. What about the next test? Well, we will also want a test for the method. So how about something like can call factorize. Alright. And here we're gonna go and do the same. Factorizer is equal to new prime factorizer. Okay, lovely. So we've got that, and then we're gonna go factorizer.factorize. Okay, just like how we want to call it. We're not going to bother with any arguments just yet. Okay, we're not going to worry too much about return values either. We just kind of want to stand up this particular method on the prime factorizer class. And let's just use Visual Studio here. Bang, public void factorize. That looks good. Okay, we've got another implemented exception. That's probably not going to help. But let's run all our tests. If I had Visual Studio Enterprise, I could set it up so that the the tests would run all the time. Unfortunately, I don't have that, so we'll have to run them manually, but it can be done. Okay, you know what? I'm gonna come along here and we're going to go, yeah, let's do a vertical document group. Nice. Okay, with the tests on the excuse me, the tests on the left and our implementation code or production code on the right, and nothing in factorize just yet, which is fine. Let's just see whether prime factorize the tests are working. Yes, they are, which is great. Okay, so these two tests were all about standing up the class and its method. Now we can start on the tests proper. Alright, so let's kind of do that. Let's kind of go public void. Okay, what are we going to do? Well, we probably want to start with 1, right? So we're going to factorize all positive integers. The first, as in natural numbers. So not 0, not negatives, but 1, 2, 3, 4, 5, and so on. So why don't we kind of go factorize 1, and with 1, what are we going to receive? So, well, with 1 isn't a prime number, so therefore we would actually expect to receive like an empty set. Okay, so empty set or list. Alright, what does that mean in reality? Var factorizer is equal to new prime factorizer. Lovely. And factorizer dot factorize, and we're going to have a 1 kind of coming in here. Okay, so yes, it doesn't have a parameter yet, so therefore our argument of 1 is going to be problematic, but it's okay. So we're going to get return values as well. Why don't we call that factors? Alright, well, we haven't got that either. And then when it comes to this factors, let's do our assertion dot should be empty. Okay, that's pretty cool. So empty would be for a collection. It's interesting that it's picked that. Let's fix things first. So factorize will need to take an integer parameter. So int, it's going to call it in, keep it nice and short. And okay, n is 1. Factors, so we're going to have not just an int, we're going to have some sort of collection. They're going to be order of sort, so how about list of int, and we want to program against interfaces, not a particular implementation, so we're going to make it an I list. Factorize is now complaining because not all paths are returning a value. You know what, I just want to see it fail at runtime, so I'm just going to, instead of returning the passing value, which is just creating a new list which is actually empty, I'm just going to return a null. We no longer want to maintain this particular test. It was only there to stand up factorize. We don't want to maintain it and like add parameters in after the fact. And we're no longer interested in this test here either, because we can create the prime factorizer, we can instantiate it, like we've done here. So these two tests are now superfluous. Let me remove them. And we're back down to 1 test. It's okay to remove tests when they no longer serve a purpose. And those no longer serve a purpose. We can create a prime factorizer, we can call factorize method, and in fact we're now we've altered the factorize method to give it a parameter, which we've got and return some values as well, the sort of list of integers. Cool. Let's just see what that does. That should fail. There we go. And it's saying something like, expected to be empty, but actually found null. Well, how do we fix that? Well, we're just going to go new list of int. There we go. That's an empty list. I'm going to go nice. Cool. oh, maybe we can condense this a little bit. So now we're at we had red compile time, we had red runtime. Okay, so when it just kind of failed with, hey, it was a null, but actually we expected an empty list. Now it's green, and let's look at refactoring. You know what? I know this is sort of following the arrange, which is what we've got here, the act and the assert. Oops. However, I mean, why don't we make this all a little bit tighter? Maybe kind of say, this is the return value, so we no longer need that, we no longer need that, and we no longer actually need the factors either. Here we go. So we, what have we done? So just put it on one line. Instantiate prime factorizer, call factorize on it with regards to the given n, and then it should be empty. All right, see whether the test is still passing. Okay, excellent. We are looking good. Next test. Well, I imagine that it would be worth our while to continue with the next integer, which of course would be 2. So factorize, oops, 2. Okay, and well, 2 is 2 times 1 is 1 times 2. So 2 is a prime number. It's in fact the only prime number that's even, the only even prime number. And we're going to have new prime factorizer dot factorize, lovely, 2 dot should. No, we don't want it to be empty. Now I think there should be an equals, I wouldn't say equal, and INumerable expected. So if we should probably kind of go, 2, and we can extend that into lists. So these are the elements. Good. Factorize should be equal to 2. That's its only factor. Nope. All right, let me run all tests. Okay, it's failing, which is good. We want it to fail. The test is red, and we want to turn it green. Let's have a look over here at the code here. I'm going to extract this into a var factors. Okay, and return factors. Lovely. And well, okay, if I was to run it, the behavior hasn't changed, so the tests are still failing the same way. One is the empty set, which is fine, but now we kind of want to say, hey, if n is 2, then we want to do something else. Well, yeah, maybe something like, I wonder what's, okay, factors.add 2. Okay, this looks good. So when n is 1, we don't come in here, we don't add anything, and we still end up at the empty list, but when n is equal to 2, then we add 2. So we had a very simple test, and now we're adding very simple production code. Okay, as even checking for hard-coded values like n is equal to 2, it seems like checking against magic numbers. That's cool. As the tests get more specific and we add more of them, the code, our production code, will become more generic. All right, let's just see where we're at here. Lovely. All right. Anything to refactor? Well, at this stage, probably not. So let's move on. Public factorize 3 is 3. Yeah, that's actually well determined here by the AI. Dot factorize 3 dot should be equal to 3. Nice. Let's just see where this leaves us. It should fail. It would be a huge surprise if it passed. Okay, it says collection expected to be equal to 3 but found empty collection. Well, I mean, that makes a lot of sense. It wasn't 2. We could just say, hey, if n is equal to 2 and if n is equal to 3, we could do that, kind of like this. 3, and 3, and that would probably work. Let me just kind of try it. But that wouldn't be particularly generic. So why don't we do this a bit different? We're checking for a value and then we're adding that same value into our collection. So how about if in, and it's, I mean, these values seem to be greater than 1, right? So why don't we make this greater than 1? Then we add the value itself. So then we add in. Let me remove that. Let's just see how we go here. Hopefully that'll pass. Excellent. And we're laughing. Let's move on. Nothing to refactor. No, that looks good. Fact. Public factorize 4 is 4. No, that's not quite right. 4 is in fact 2 and 2. 4 is the first factor which isn't a prime number and is in fact the product of 2 times 2. So let's look at that. New prime factorizer dot factorize, and we give it 4 dot should be equal to 4. No, 2 comma 2. Great, so that's quite nice, isn't it? All right, let's see what happens. Aha, the test failed, which is good. We wanted to fail. There we go. Expect the collection to be equal to 2, 2, but found 4. So, well, so we're checking for n is greater than 1, and then factors that add in. Yeah, well, that's not going to work. We kind of like need to divide by 2 and then add the remainder. So it's still the factors that add in might still kind of work for us. Let me just kind of, but you know, up here we probably want to do something like if, okay, we're back at the n, because it is equal to 2. No, we probably want to go with something a little bit more generic. Modulus of 2 is equal to 0. That means that if n divides by 2 and doesn't leave a remainder, which means it cleanly divides by 2. All right, when we've got that, then what do we want to do? We want to go factors dot add, not n divided by 2. We want to add 2. That's cool, but we also need to reduce n by that factor. So we need to reduce n by 2. So n divided equals 2. I think we can do it like that. And then factors add in. So, okay, what does this mean? We check. So we've got 4 coming in. Yes, it's greater than 1. 4 divides by 2 and leaves a remainder of 0. Fantastic. So it means we add 2, we divide n by 4, so we divide 4 by 2, which leaves 2, which we add, and then we'll have 2 and 2. Okay, this is nice. Let's just run all tests. Right, so factorize 4 works, but 2 doesn't. Okay, and why is that? So when n is equal to 2, n is greater than 1, n divides by 2, lovely, and then we add 2, but then we divide 2 by 2, which is 1, and then we add 1. Yes, so that's not so good. Expect the collection equal to 2, but find 2 comma 1. Let's put on a little bit of a hack here. If n is greater than 1, then we add the n. So for 4, we'll add 2. 4, when it's 2, we won't add the 1. I think that'll work. Fingers crossed. Nice. Okay. So we've got a couple of prime numbers already, 2 and 3. Let's we probably don't need to do 5, but you know what, let's give 5 a go. Okay, no, I love it. The AI kind of gets it right. Factorize 5 is 5 because 5 is a it's a prime number. So 5 times 1 is 5, and 1 times 5 is also 5. So so 5 is a prime number. Factorizer dot factorize 5 dot should dot equal no, not 2 and 2. I wonder where it gets that from. 1 as a 5, sorry. That should just work out of the box, hopefully. And there's no problem with the test working out of the box. Okay, cool. We probably don't need to do any more prime numbers. I would expect them to just work now. 6 is interesting because that's also 2 factors. 6 is 2 times 3, and or 3 times 2. But these are different. Unlike 4, we had 2 and 2. Let's just see what it works out with. Factorize 6 is 2 and 3. Okay, lovely. New prime factorizer dot factorize 6 should be equal to 6. No, 2 comma 3. So these are the factors are ordered from smallest to largest. So 3 comma 2 wouldn't work. We are checking on the particular order as well. I think that should work. So we divide by 2 and then we add 3 in as well. And okay, that works. 7 is fairly boring. Let's give that a miss, but 8 is cool. 8 is 2 times 2 times 2, and we haven't had a number with 3 factors yet, especially 3 that are the same. So facts, okay, oops, public void factorize and 8, is 2, 2, 2. Lovely. Okay, prime factorizer dot factorize. We've taken the 8, and this should be equal to 2 comma 2. Yeah, nearly. We're on the right track. Another 2 in there. Lovely. Might probably won't work. I'd be surprised if that worked. No. Yeah, expected 2 comma 2 comma 2, but found 2 comma 4. Alright, let's remove those excess using statements. They are not required. Alright, it's kind of come down to here. What's happening? We kind of come in here. 8, divides by 2 cleanly. We add the 2. And we divide 8 by 2 is 4, which of course we're then adding as well. It's almost like we need to have another one of these. Okay, let's just see whether that works. All right. Yes, it does, but this isn't particularly useful. We can't kind of keep adding, for 16 or, 32, 64, where we've got a large number of 2s. We really kind of can't keep on adding these if statements on there. We want to sort of execute any number of these ifs, and we've got that, right? So if a repeated if statement is a while loop. So while n divides by 2, kind of keep adding the factor of 2 and keep dividing by 2. So with 8, it should kind of divide by 2 again, and this ought to work. Let's give that a go. Lovely, it's working. With regards to refactoring, maybe one of the things we can refactor is we pull this if statement out of here to make it a little bit simpler. I didn't really want to have that in here. That shouldn't change the behavior. And in order, it's really easy to check whether or not it's changed the behavior. We just run all of our tests. Bang, tests will pass. This hasn't made a difference. It's the final factor, so that's fine. What's the next number? I think 9 ought to be interesting, because 9 is 3 times fact. Public void factorize. 9, of course, is 3 and 3. Great. So new prime factorizer dot factorize 9, and that should be, should equal. Okay, what did it come up with? No, that's not, that won't do it all. 3,3. Those are the factors. 3 and 3. 3 and 3 makes 3 threes is 9. Lovely. See what that works. Yeah, I don't think that's going to work. Okay. Alright, what are we meant to do about that? Well, it's almost like, what we're doing here with the 2s? We want to do the same thing with 3s. Kind of like, hey, let's take all 3s and kind of, and then and maybe 5s and 7s and so on. Okay, this is probably not going to, this will pass, but once again, it's too manual. What do we do with, and if we sort of kind of compare, that's why I like to start out like this, because we can sort of see where we need to make changes. So 2, 2 and 2, and 3, 3 and 3. I think what we will need is something like a var divisor, which is 2. Okay, this divisor, well, we start with 2, plonk it there, and here. And then we want to increment that to 3. So let me just kind of remove this. Divisor plus, something like that. Yep, that looks good. And then, of course, we want to repeat this any number of times. So pretty much while n is greater than 1, so while n is greater than 1, and of course this var divisor needs to be pulled out, otherwise we're going to be stuck at 2. Yeah, that looks pretty good. Let me quickly run all the tests and see whether it works. Okay, so it works for 9 still, and all the other tests pass as well. It looks like we no longer need this n greater than 1 check, because we're doing the while n greater than 1. So we're never going to come out of here unless n is in fact 1. We can remove that. So it's a bit of simplification, which is nice. And lovely. So it's working for 9. And I would say that it probably ought to work for all values now. So let's do a fact public, void factorize, maybe acceptance test. Okay, and we're going to go new prime factorizer dot factorize, and what we're going to do is we're going to build up a number here. We're going to say 2 times 2 times 2 times 3 times 3 times 5 times 7 times 11 times 19 times 41. There you go. I find that a bit hard to read. I'm going to put a bit of spaces in there. I should start at the other end. Being easier. Okay, cool. And of course, we know what that factorizes to. I'm going to grab that. That factorizes, in fact, to the very same list. So should dot equal, well, you know, all these guys, but now with commas. Comma. There you go. That's actually a nice way of doing it. We're kind of building up the integer by multiplying together a number of prime factors that are known to us, and then we're checking that we get those prime factors, you know, repeated back to us. There we go. Should equal. Nice. Okay, let's see whether this works. And lovely. Okay, look, we get success for all of our tests. Our acceptance test is working, so we get the prime numbers that we expect. I mean, I think this is actually a reasonably easy to understand algorithm, if you will. There is a way of condensing it further, which arguably removes some of the readability, and the way to do that is to move the while loops into more concise, although probably slightly harder to read for loops. So let's kind of do that. Let's start with the outside loop. So if we turn that into a for loop, okay, from the while, the inner condition is the iterator condition, and what we've got up here, the var divisor 2, is in fact our initial condition. So var divisor 2 is initial condition, our iterator condition goes in the middle, and then so the checking condition and the iterator condition is a divisor plus plus. Let's kind of chuck that in here. Let me just make sure it's all still okay. The tests are still working. Lovely. I haven't screwed anything up. That's the beauty of it. Just kind of run the unit tests. If it's all good, we're good. And what about the inner loop? We can turn this into a for loop as well. So for what are the initial conditions? Well, there isn't any, other than that we receive the in and the divisor as they stand. Then this is the condition that we check against, and then sort of the way we iterate is the way we reduce the in by the divisor, like so. Okay, let me quickly check that I haven't screwed anything up. Hold on. Run all tests. Lovely, it's all still working. And of course, this also means that we can remove the brackets and just make it terser still. There we go. A couple of nested for loops with factors that add divisor. We're done. All right, this is lovely. And it's all still working. I've had one person to kind of say, well, hold on, the way we're sort of, iterating over the divisors, but just kind of going, incrementing them by 1, that means you have 2, 3, but then we've also got 4, which is not a prime number. Isn't this a problem? No, it isn't, because 4 is 2 times 2. We've already removed all factors of 4. Therefore, that division will immediately fail, and we can move on to the next number, which is 5, which is a prime number. Right, and this will work just fine. Then that's one little inefficiency. Okay, the other one is that maybe we don't need to always run out immediately to the length of n. So for example, if we've got a number like 34, which is 2 times 17, those are the only two factors. When we when we hit 2, and then we get up to the roughly the square root of 34. Well, let's kind of choose 36, which is in the vicinity, a little bit larger. The square root of 36 is 6. So when we kind of go up from the factors 2 all the way up to 6, we can actually then forego dividing all the way up to 34, because you can't have two divisors that are both larger than the square root. If you multiply two divisors that are larger than the square root, like 6 and 6, we already end up with a number that is larger than our original n, and therefore it's problematic. So once you reach the square root of 6, you can stop. You could terminate, and then whatever number is left is the other remaining the last remaining prime number, and you can kind of use that. Doesn't apply all the time. Most of the time, I would imagine the algorithm finishes before it kind of gets to that, but from time to time, when you've got sort of numbers that are have got one really large prime number multiplied by one or a bunch of smaller prime numbers, you might find that the algorithm takes a little bit longer and is inefficient. But there you go. You've got the sieve of Aristophanes and the Greek fellow who kind of came up with this, so like 2,000 plus years ago, and feel free to give this a go yourself. But we're done.